What's up, everybody? It is Mr. Prevet back again with the 2021 FRQ. And we're looking at question number 1 today, starting out the year. And it should be pretty awesome. We got a table, and this is a calculator question. So, table calculator questions should be interesting, right? Might be a little complicated. We'll figure it out together. But as always, thank you guys so much for watching the videos. It means a lot to me that y'all would. And I really just hope that I'm helping you get better at calculus. That's my goal. I want you guys to succeed on the AP exam. So let's go ahead and take a look at question 1 together. Let's read it. It says the density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. Okay, so it's like a density, right? Milligrams per square centimeter. Values of f of r for selected values of r are given in the table above. Okay, so we got this table, and at these different points for a radius, where a radius is 0, 1, 2, 2.5, and 4, they give us the density at that point. Okay, so let's figure this out. Part A, what does it ask us? It says use the data in the table to estimate f prime of 2.25. Okay. Now, this is like an instantaneous rate of change, right? This is f prime of r. And a really great approximation for an instantaneous rate of change is an average rate of change with two endpoints that are really close to it. We want to make the interval as small as possible with our point right in between it, right? So we look and we have values for when r equals 2 and r equals 2.5. So I know that a good approximation for f prime of 2.25 will be the average rate of change from 2.5 to 2. So that would be f of 2.5 minus f of 2 divided by 2.5 minus 2, which is equal to 10 minus 6 divided by 0.5, which is 4 over 0.5, which equals 8. Now this 8, what does it actually mean, right? What's the context? You get a value, but it says specifically to interpret the meaning of your answer in the context of the problem. Let's think about this. We have a function f of r, which is in milligrams per square centimeter, right? And we're taking the derivative with respect to r. So our units of this are going to be milligrams per centimeter cubed, right? Because we're in milligrams per square centimeter, and then we're doing that per centimeter when we take the derivative. So it's per centimeter cubed, right? Now, in the context of the problem, what we are saying is when our radius from the center is 2.25 centimeters. It's a rate of change, right? So our rate of change of the density of the bacteria is 8 milligrams per centimeter cubed. So all we're telling them is, hey, we know that as we're going from the inside out to a radius of 2.25 centimeters, a rate of change of the density, because it's f prime of 2.25, of the density of the bacteria is 8 milligrams per centimeter cubed. And that should be plenty to earn you um, this point, right? So, not too difficult. But that's part A. Yeah, I think the first step is really easy, right? Just this approximation. Maybe the unit's a little shaky, but the interpretation is what I would suspect might trip people up for this one. It's hard to use this much vocabulary. It's almost like a reading test, right? Do you understand what the question is saying rather than like actual math? But the AP loves to be concept heavy, so it's important that we nail down these ideas in our head. But that's part A. Let's move on to part B. We haven't even used the calculator yet, so I assume that on these later parts they're going to use it a ton, but we'll see if that's true or not. Let's look at part B. So part B says the total mass in milligrams of bacteria in the petri dish is given by the integral expression 2 pi times the integral from 0 to 4 of r times the f of r dr. Okay, so that's our radius times our density. We're integrating that over our radius and then multiplying by 2 pi. Okay, and it says approximate the total of that integral using a Wright-Riemann sum with 4 subintervals indicated by the data in the table. So for a Riemann sum, our subintervals are based on our R values. For us, it looks like we're going from 0 to 1, 1 to 2, 2 to 2.5, 2.5 to 4. So what we're going to do is multiply our length of our interval by the value of the function on the right side. That's why it's a Wright-Riemann sum. And then we're going to multiply that by 2 pi, right? Now we gotta be careful. For this, we'll have 2 pi kind of on the outside of all of this, and we'll just multiply it out in the end. But on the inside, right, the length of my first interval is from 0 to 1, right? So my length of the interval is 1. Now, what's my value of the function? Well, f of r is equal to 2, so I might be tempted to just say 2. But our value that we're looking at is r times f of r. Now, we get lucky in this case because at the right endpoint, r is equal to 1 and f of r is equal to 2. So r times f of r is equal to 2. So this is the length of our interval times our value of our function. Let's do the next interval. The next one is from 1 to 2. So the length, once again, is equal to 1. But our value is going to be a little different, right? Because f of 2, our right endpoint, is equal to 6. And r is equal to 2. So r times f of r is equal to 12. Our next one, our length of the interval is 0.5. F of r is equal to 10. R is equal to 2.5. Multiply those together to get 25. And I'm out of room, so I'll just add it in right here. Our final interval has a length of 1.5. And its value is going to be 18 times 4, which is 72. Now, you could either do this in your calculator, type all this stuff out. I like doing some arithmetic just for the sake of it, so I'll multiply this out. I get 2 plus 12. Half of 25 is 12.5, and 1.5 times 72 is 108. So I get 2 pi times 14 plus 12.5 plus 108, which will come out to, hopefully I get this right, 134.5. It would be really awkward if I didn't, so I'm just going to bank on that being correct. And that is equal to 269 pi. And I'm sure if you guys gave this, just as a decimal approximation, they would be completely fine with that, no issues either way. But Let's see. Does it ask us to give any units? Well, we could think about it. It tells us the total mass in milligrams is given by the integral expression. So our units on this would be milligrams. And that would be our final answer. So part B is just doing a Riemann sum. This one's weird though, right? Because we have R times f of R. Normally there's just one function on the inside of these approximations. So this is a good switch up showing us that, we can have different values other than just the ones that are in the table. It could be R squared f of R. Then we would need to square our right endpoints, R value. So interesting question. I really did like this one. But that's all we got for part B, so we'll move on to part C. We're speeding along pretty nicely on this one. I say that as we're 11 minutes into this video, so maybe I need to speed things up just a little bit. So let's keep it moving. Part C. Let's check this one out. It says, is the approximation found in part B an overestimate or underestimate of the total mass of bacteria in the Petri dish? Explain your reasoning. Now let's think about this. Riemann approximations. When do they over versus under approximate? Well, this is a right Riemann sum specifically. And if our function was increasing, a right Riemann sum we know uses the right value to approximate. So if I were to draw out an example, this clearly over approximates. If I drew a decreasing function, right, a right Riemann sum clearly under approximate. So all we need to figure out is this function increasing or decreasing? And that will tell us if the Riemann sum is an over or under approximation. Now, we know that we are trying to approximate this 2 pi times the integral from 0 to 4 r times f of r dr, right? So the Riemann sum, right, for this function, the function that we're actually integrating, because 2 pi is positive, is this r f of r deal. That's what really matters. Is r times the f of r increasing or decreasing? Let's think about it. As we go to the right, as our r gets bigger, is r going to be positive or negative all the time? Is it increasing or decreasing? Well, r is definitely increasing, right? Because as our r gets greater, we're going in the right direction in terms of r values, r is going to be increasing. Now, f of r, we don't really know, right? Is f of r getting bigger or smaller? We look at our table, it definitely looks like f of r is increasing, but that's only at certain points. But thankfully, in the instructions to the problem, they tell us that f of r is an increasing differentiable function. So, because f of r and r are both increasing functions, that means that r times f of r is also an increasing function. So therefore, this approximation will be an over approximation for the value of this integral. I guess they use overestimate, probably easier to write out than that. But that would be our final answer. So that would be great for part C. Moving on to part D, which you can always assume is going to be quite a stinker, especially with calculators. Normally it's going to be some ugly expression or something like that. Let's check it out. We haven't used the calculator yet, and we're 3 parts through. So if this one doesn't use the calculator, we might be doing something wrong ourselves, But let's take a look. The density of the Petri dish, or of bacteria in the Petri dish, for r between 1 and 4 is modeled by the function g, defined by g of r equals 2 minus, and this is where we're going to use the calculator, the cosine of, holy cow, 1.57 root r, I can't even finish writing it, goodness, cubed, holy cow. It says for what value k, where k is between 1 and 4, is g of k equal to the average value of g of r over the interval from 1 to 4. Okay, so man, this is an intimidating function, but thankfully we have a trusty calculator by our side. So it doesn't matter how ugly the function is, right? But we're trying to figure out where g of k is equal to the average value. So first thing we could solve for is the average value of this function. We know that the average value of the function is the integral from a to b, which in this case is 1 to 4, of that function divided by the length of the interval. And I can do this using my calculator. One really awesome tool is if you click math and go down to number 9, we get this function int, and it allows us to calculate definite integrals. So I'll go from 1 to 4, and now I need to type out my g of r, which is this whole ball of nastiness. So let me type it out. 2 minus 16 times cosine of 1.57 square root. I'm going to use x instead of r. Doesn't matter which variable you use as long as it's consistent. So it's the cosine of that cubed, another parentheses, dx. Let me make sure I got 3 parentheses on that side. I got 1, 2, 3 parentheses on that side. Okay, so I'm feeling good. I click enter, and I get this value, 29.62. But I need to divide that by 4 minus 1, which is equal to 3. So I get this value, and that is what g of k has to equal. G of k has to equal 9.87. We'll round it up to 6. Okay, so now I just need to figure out where is my function g equal to this, right? And the best way that I've found to do this is by isolating 0 and then graphing the function. So if I subtract this over, and I get g of k minus 9.876 equals 0, I can graph this function and then use my second calc, to find the value where this equals 0, where it crosses the x-axis. So let's go to y equals. Let's type in this function, g of k minus 9.876. So I'll do it 2 minus, you gotta type this whole monstrosity in there again, cosine of 1.57 root x. Gotta put parentheses, another parentheses. Do we need another one? No. Yes, we do. We need a third one. Raise that to the third power. But then we are going to subtract that 9.876. I'm going to graph this. Now my window is quite a bit off, right? Obviously my window's a little messed up, but I know that my r value is going from 1 to 4. So I'm going to make my x minimum value 1, my x maximum value 4. So now when I graph it, okay, see, now I got kind of like the perfect value, right? I can see that I only cross the x-axis at this one point, and that will tell me when this function is equal to 0, what k is equal to. And I can solve for that by doing second calc, like I was saying, go down to 0. I get a left bound and a right bound. I click enter, approximate, boom, 2.497. And that is our final answer. So that is the value k, which is a radius, right? The makes it to where our instantaneous, right, g of r is equal to my average g of r, right? So that is our final answer. So that is all we got for question number 1. A really interesting calculator question. I like this one a lot. Definitely a bit complicated in some places, but totally doable. I love the way it approached the Riemann sums, not just having it be one function. And the units and context of part A were really great. Part D, this calculator question was also cool. Big fan of this question. If you can answer this question, you can answer anything. Straight up, this is a challenging, thought-provoking question, and I think it's just fantastic. So I'm glad that I was able to go through this with you guys. I hope that you guys keep practicing, getting better at calculus, and I will see y'all in the next video.